Um, well, as I think every time I listen to Peter's lecture, I decide to rearrange my own. So I feel like, although we changed the schedule around completely today, I would like to change it around again. Even maybe like in the middle of the talk, I would just change it into some other talk. Um, I feel, as Peter was talking, I thought, oh, I was reminded that there's so much more to say about some of these topics. And then I thought, well, we should remove some topics and add some more topics. Um, so I would, if people are happy with it, I would propose almost eliminating my stories about thermal noise tomorrow, and I'll still leave in the part about the optics part of it, which is how to make the dielectric coatings on optics, how coating design can be done, but then I'll leave out all this fanciness about noise cancellation within, thermal noise cancellation within coatings. I think it's too fancy. And then I thought on this thing, I would use this time to talk a little bit about geometry and all these things, but then I'm not so sure about this anymore. This is something that you can read on Wikipedia. So you don't have to decide now, but I'll be ready tomorrow to talk either about this or this transfer matrix. You can read about almost everything on Wikipedia, but I feel like I can add something to what Wikipedia's wisdom is in this category and this category, but maybe not in these. You don't get much use from me deriving Hermite-Gaussian polynomials for you or something. You can get that from the excellent book by Siegmann or Yariv. This thing I can talk a little bit about. This is easy. And the ABCD matrix approach, please look it up for yourselves and then see if there's some confusion. I'm happy to talk about it, but it's not so illuminating. What I can say is not so illuminating. So what I wanted to do is repeat this Fabry-Perot fields derivation in a slightly different way, and then repeat it yet again in like even more different way for some reason. So you should get the feeling that on the third repetition, why would somebody repeat a derivation 3 times? Somebody like me who doesn't derive anything. Somehow I feel like the third way is so important that it's worth describing it to you. So this second way is not, there's what you just heard, which is fine. And then if you remember from your quantum mechanics class, there's another way to do these things where I think what Peter described is what I learned also in electromagnetism class. It's in several books anyway, this infinite sum technique. But if you remember early chapters in quantum mechanics, when you do the finite square well, there's something like this, and you say there's a plane wave entering from here, and then you say, in here, what can happen? Maybe there's some sort of bound wave, and then there's something going like this, and there could also be something coming in from this way and going out that way. And so you solve a kind of self-consistent field equations. You say here the potential is 0, and here the potential is something like this. And then at the boundary here, you have to make the field be continuous, and the discontinuity in the discontinuity in the derivative can be due to this change in this, and the wave vector changes because of the potential. And so I think this is a technique everyone remembers vaguely. Yes. Yes. So for the Fabry-Perot cavity, there's the same thing, and you can. I think mainly I did poorly in that part of the math class where we're supposed to learn how to do infinite sums. That's why I talk about this. So this mirror, remember, this is R1, T1. This says R2, T2. And so you can do the same thing. You say there's a wave like this and a wave like this. Right? Like this. And so you can label them. We can label them like this. E1, E2. What's crazy labeling? E3, E5, E4. And if you take a few minutes, you can. I invite you to do this calculation for yourself. I'll just set it up, but you should do it for yourself. So you say, what's the relationship here? Between this one and this one, I get this one transmission and I get this one phase. So I can say E3 is equal to E1 times T1 e to the minus I phi. And then it also has this piece that this field bounces off here and goes here. So here I get a minus sign for this reflection. So it's E5, R1, and then also one phase, e to the minus I phi. Right? Okay, this is okay, but now I can't solve for this field because I don't have this one. So what is this one? This one is just going to be related to that one, right? E5 is equal to R2 E3 e to the minus I phi. And so you see how this is going. So you can write down a few equations that relate this to this and do some substitution and make them equal to each other. So I'll pause for 3 minutes. That should be enough. I'll give you 3. If you're interested in 3 minutes, you can do some algebra here, and what we'd like to find is what Peter just showed, and find out what's the formula for E4 in terms of E1 and what's E2 in terms of E1. As a group, we are 50%. That's my estimation of, that's the progress bar that I see when I look up at this. I think the only tricky thing could be something about these minus signs. So, so in this labeling, phi is equal to KL, so that's the phase shift you get. And then there's something about minus signs. And there's one convention that takes it when you transmit and reflect through mirrors, you multiply by I, but you know, it's all a little bit fake. But in here, the convention I'm taking is that when you reflect from air off of a material which has a higher index, I assign a minus sign to the reflected field. And when you're instead reflecting within this glass, so it's high index to low index, I say there's no minus sign. So that's why here there's no minus sign, and here there is minus sign. And then for transmissions, I don't put any minus sign. And that way the power is conserved. In reality, there's no such simple thing like this because all dielectric coatings give some overall phase shift, which we don't know, but that's just convention. Anyway, I assume you've mostly got it. Um, the common term that you see when you do these things is this thing in the denominator, which is this 1 minus r1 r2 e to the minus I2 phi. And what you'll see when we talk about feedback tomorrow, I think tomorrow, yeah, that there will be a similar term. And the signal as it travels once around the feedback loop is identical to this. This is just talking about the round trip propagator. That normally you would just have this term, but because of feedback you get this. Anyway, so you can see from working this out, there'll be some cases in which the infinite series is the way to go, and some in which this is the way to go, and it sort of depends on the details of the algebra. Anyway, so that's not what I wanted to tell you about. I was just saying, look at this nice Fabry-Pro picture I've drawn, but and then this is one thing you could do. What I wanted to tell you about is this other technique, which is way cooler than what you've just done. And the purpose of you doing this thing on paper is so that you feel the pain of infinite sums and this other algebra technique, and then you see this technique, and it's like the sky has opened and the sun finally came out from behind the clouds. What is this technique? So we have a bunch of equations and there's some unknowns. And whenever that happens, if you've taken linear algebra, you say, what is the matrix? And that's really the question. And you can't be told about it. You just have to see it for yourself. And this is the matrix for how you calculate the fields within a Fabry-Pro interferometer. And let me decode it for you now. So here, this 1 corresponds to the rows, maybe? Yeah, rows, columns. So the elements in here correspond to something like, if I go from node 1 here to node 2, what's the thing that I write down for this single hop coefficient? So you don't have to do any algebra here. You just write down the drawing. So you say, if I go from 1 to 2, what is there? There's a reflection, R1. Good, done. What else is there? Well, 1 connects to 2 by this, and 1 connects to 3, and that's it. So from 1 to 3, all I have to write down is this phase shift. First this transmission, T1, and then this phase shift. And then it goes here. That's it. Node 1 doesn't connect directly to any of these. It connects to the other nodes through the other nodes, but in the direct sense, that's it. So you put zeros for everywhere else. That's all it does. And the matrix is 5 by 5 because I've chosen to write down 5 nodes, but you can see, because in some places I have 2 terms, of course it's a little bit, I've already done some shorthand. And really, this node connects to this node, but I just didn't label this one because between here and here, it's always going to be e to the minus I phi. But if I wanted to be truly pedantic, I would have made this one and this one labeled, and I would have had a 7 by 7 matrix, which is also fine and probably better to do. But anyway, just to fit it onto the screen and everything, I did this. So anyway, that's this. You can go through here, 2 to 2. 2 just goes out there. It doesn't connect anywhere. So 2 is blank. 4 also just goes off the board. It's blank. 3 goes to 4, and 3 goes to 5. So I have this one. T2 goes there, and then this guy connects here through this minus R2 and e to the minus I phi, and so on. So you see, this step is nothing. It's just a matter of clearly drawing it on your piece of paper and then making the connections one-to-one. And so far, there's no magic. This is just a way of accounting for all of the terms. But the next step is magic, which and the magic of why it works, you'll only see truly when Peter talks about feedback tomorrow, but it has to do with this thing. This denominator, this 1 minus R1, R2, e to the minus I2 phi, this is the propagator. And what it means is that if you inject a field at any point in here, and you want to find out what the resulting field will be here. So you put in a field, and what will be, after all feedback is done, what will be the final field? What you do is you write down usually what we know as the closed loop gain equation for loops that will turn out to be 1 over 1 minus g, which means that what's the total round trip propagator. And g encodes all of the possible paths that your signal can take and return back to this similar node. And for optics, what we write down is the following. 1 over 1 minus m, where m is the round trip propagator that includes all of the nodes. And this I is the identity matrix. So really what we're doing is doing the matrix inverse of this operation. And in fact, this is the same thing that we do when we want if we wanted to do algebra for multiple feedback loops. It's all of the same. Multiple feedback loops, multiple path, Fabry-Perot matrix, whatever. So we can do that. And let me see if I can. Oh. Yeah. This is so difficult. Yeah, so I did this here in Mathematica. I wrote down the matrix. First time I wrote it down, I did it transpose, so I did transpose operation here. And then I type it matrix form. So this is just what I've shown you before on the keynote. And then here I do just what I said. I said, take the identity matrix, 5 by 5 identity matrix, and do it. So I do it there, and Mathematica gives me this. And then this has nothing to do with optics, but just an interesting Mathematica trivia. You can say copy as LaTeX. Yeah, I've just learned this. And then you can copy it into this program called LaTeX it. LaTeX gives you an image, and then you can put it into this slide format. So that's, I didn't type in all of this into some equation editor in PowerPoint. So just so you know. Okay, so now this is it. So in one step, we've found every single node-to-node transfer function within the 5-node system. So there must be a connection 5 to 2. It's node 5 and 2. So 5, 2. Yeah. Yeah, did I not write that down? Yeah, this one? No, second column. Fifth to second column. Connection of E1 is column, but not row. There is a connection between 2 and 5, so it won't be repeated in... No, it's just here. This is 5 to 2 and this is 5 to 3. Yes. So it won't be repeated in 2, 5. No, 2 goes this way. Yeah, if we reverse time, it would be as you say. So then 2 would go to 5. Yeah, that can be done too. So that's useful to do if you went backwards in the other direction. So, and we will. That's sort of the magic of. I haven't shown you the full magic. That's next. Yeah. So anyway, so Fabry-Perot cavities. This is very nice. I take the identity matrix. I multiply this thing. I do this in Mathematica, of course. I can only invert 2 by 2 matrix myself. So this does it. But anyway, in one shot, you get all of the ones you want. So if you wanted to find out with full feedback on, you inject a signal into 5 and what shows up at 4 or what shows up at 2, all of these things are in here. For example, I inject a signal into 1, what shows up at 1? That's just 1. Nothing else happens, of course. Same thing goes for 2 to 2. If I stick something in here and goes this way, nothing else happens. You see here for like 3 and 5, it's different though. If I stick a signal into here or into here, I have to take into account the fact that the field bounces around within the cavity, and so there's some sort of feedback effect. And this is this feedback propagator, the 1 over 1 minus g that I was talking about that we've seen before. So that's 3 and 5. And anyway, similarly, you can find them. We were trying to calculate this equation for the transmission, how 1 goes to 4. What's 1 goes to 4 here? Maybe I get it wrong. I think this one is. So 1, 2, 3, 4. So there's the equation for 1 goes to 4. So this gives you the transmission of the cavity. And there's similarly, there should be, yeah, this 1 goes to 2 here. So, okay. That's kind of cute. So it's a kind of algebraic shorthand for us to get the equation that allows us to tell us what the field is anywhere within the Fabry-Perot cavity. But now, I didn't draw it because it takes too long to draw figures of this kind. But you can see exactly what you could do if you wanted to. There's nothing that limits you to a single Fabry-Perot cavity. Now, if you want to, you can write down the same thing for the full system, 2 Fabry-Perot cavities, power cycling, signal recycling, multiple compound this, speed meters, whatever you feel like. And the computational complexity is nothing for you because all you have to do is do this, and then Mathematica does the inverse. And doing this is no more difficult for 6 cavities, 2 cavities, whatever. In each case, you just have to be careful to write down the single hop term. And that will always just be something like a single phase shift or a single transmission or that kind of thing. You can do it everywhere. And why do you want to do that? Of course, the first reason you want to do that is just to find out what are the conditions for getting resonance, how do you get your signals to build up. But then later on, we want to do more complicated things. Of course, we don't want to just do static field calculations. We'd like to do audio frequency response and say, if I do something like shake this mirror, and let's say it's the end mirror, then how does that build up in the full resonance system? Well, it's just these equations again, except for now this phi encodes not just the phase due to the normal laser wavelength, but also the fact that you've put on this audio frequency modulation. The introduction of the introduction of audio frequency sidebands is no more complicated than anything we've seen before, because it's exactly the same as having the electro-optic modulator. If you have like what I was saying yesterday, you put a field through here, and what happens? You start off with this, and on this side you end up with some small sidebands. And we said those small sidebands would be this E0, 1 plus I gamma over 2, e to the I omega t, omega modulation. So the plus and the minus. And this is for cosine modulation. Well, you get the same thing if you have a moving mirror. If you take the field and you go in like this, and this is and I say now this thing is moving by x, and I ask, what's this field? This was E0, and this is E prime. Then what's this field that's leaving here? It's going to be the same thing, except for now the modulation depth is going to be this x, the motion of the mirror divided by lambda, or 2 pi times x over lambda or something like that. But anyway, the modulation depth is just related to how much you're truly how much phase shift this field gets on reflection from here. So that's all. So that tells you now what to do. At each place where we have this, we've calculated the static field. We've calculated the static field by this process, regardless of how complicated our system is. So we've got this E0. We know what field is entering there, and now what we want to know is, if I take this static field and I drive it by this modulation, now these audio fields will propagate throughout the system, bounce around everywhere, come back to this place, and what's the set of self-consistent equations that will tell us what is the amplitude of the audio field everywhere? Well, you just do this same matrix calculation, but you do it for these plus and minus sidebands. And in fact, as it turns out, you only have to do it for one of the sidebands, because one is just the complex conjugate of the other, so you don't have to do it for both. But if you wanted to, you can do it for both. It's just more fields. And so every time you shake any optic, it's just nothing to calculate everything, because you just type it in. You've already got it, right? The full propagator is done. When you do this once for the main field, you get it for everything. And then you just put in different frequencies, and you compute it again, and then it becomes a computational problem. If you want to calculate for 1,000 frequency points, well, you just have to calculate this matrix for 1,000 frequency points. But that's a simple thing on the computer today. But in this technique, you can then get the frequency response of anything to anywhere. You can also do the same for the gravitational wave, of course. If the gravitational wave is coming in from above, then you just say it acts as a phase modulation uniformly within this. At the same time, it phase modulates all the light within there, so you can just change the phase differentially between this cavity and the other one. And you can find what's the effect of signal recycling and moving the signal recycling mirror. You get the full frequency response with no trouble. And you can even use it for all of the noise terms we talked about. we were discussing about laser amplitude noise and laser frequency noise. And after Ollie's talk, I was saying, well, how can you be sure that this obscure coupling doesn't matter at the 7th foot frequency of it? Nobody knows these things. You just use this kind of computation and get it. And so you take as your source term way back out here this E0, and you apply phase modulation like this when you want to worry about frequency noise. Phase modulation and frequency noise are the same. And then you can just flip the sign on one of the sidebands if you'd like to do amplitude modulation. So you can do amplitude modulation, phase modulation. It's easy. Whether it's amplitude or phase is just some prefactor. And anyway, you just propagate the fields in the system. And then you can say, this laser amplitude noise gives me this kind of signal at this port E12 or E15. And the gravitational wave gives me this kind of signal at E15. And then immediately I have the signal-to-noise ratio of how much this laser noise couples to this and how much gravitational wave couples to this. That's it. Just with this one technique, the whole mystery of all of calculations of noise and signal in LIGO is kind of, it's not a, once you have Mathematica, you can do it. And then you don't even have to use Mathematica, of course. You can do this in whatever program you like. I just do it because you can graphically show what to do. So now I would move on to finesse. Any questions about this? Yeah. I'm so excited about this technique, I don't need to take a break. But the rest of it.